Classical physics, governed by Newton's laws, once seemed absolute. It described a predictable universe where objects followed precise trajectories like clockwork. However, at the atomic scale, this deterministic view collapses. Quantum mechanics reveals a realm where particles defy classical rules, behaving unpredictably. This scene contrasts the orderly macroscopic world with the chaotic quantum reality, setting the stage for the bizarre phenomena to come. In 1801, Thomas Young's double-slit experiment demonstrated light's wave-like nature, creating interference patterns. But when repeated with electrons, the same pattern emerged, even when fired one at a time. This proved particles also behave as waves, a cornerstone of quantum mechanics. The experiment challenges our intuition, showing that particles exist in multiple states until measured, a concept central to quantum theory. Werner Heisenberg's 1927 principle states that we cannot simultaneously know a particle's position and momentum with perfect accuracy. The more precisely one property is measured, the less certain the other becomes. This isn't due to technological limits, but a fundamental feature of nature. The principle shatters classical determinism, illustrating that at quantum scales, reality is inherently fuzzy and probabilistic. Erwin Schrödinger's 1935 thought experiment imagines a cat in a sealed box with a radioactive atom, a Geiger counter, and poison. Until observed, the atom exists in a superposition, decayed and not decayed, implying the cat is both alive and dead. This highlights the absurdity of applying quantum rules to macroscopic objects, sparking debates about observation's role in collapsing quantum states. When particles become entangled, their states correlate instantly, even across vast distances, a phenomenon Einstein called spooky action at a distance. In 1964, John Bell proved entanglement violates classical physics, confirming quantum non-locality. Today, it underpins quantum encryption and teleportation, showcasing how quantum weirdness enables real-world technologies. In quantum mechanics, the act of measurement alters a system's state. For example, photons change from wave-like to particle-like when detected. This observer effect suggests reality is influenced by consciousness, a controversial interpretation. Modern experiments confirm that measurement devices alone can collapse wave functions, deepening the mystery of quantum observation. Quantum tunneling allows particles to pass through energy barriers seemingly impossible to surmount. This effect explains nuclear fusion in stars and powers technologies like tunnel diodes and flash memory. Without tunneling, the sun wouldn't shine. It's a direct consequence of wave-particle duality, proving quantum particles can borrow energy to defy classical limits. Proposed by Hugh Everett in 1957, the many-worlds theory suggests every quantum decision spawns parallel universes. In one world, Schrödinger's cat lives. In another, it dies. This interpretation rejects wave function collapse, arguing all outcomes exist simultaneously in branching realities. While unproven, it inspires sci-fi and fuels debates about the multiverse's existence. Quantum computers leverage qubits, which exploit superposition and entanglement to perform calculations exponentially faster than classical bits. Companies like IBM and Google race to build practical quantum machines, promising breakthroughs in drug discovery, cryptography, and AI. Yet, challenges like decoherence remain, making quantum computing one of the 21st century's most ambitious frontiers. Quantum mechanics continues to redefine reality, from teleportation experiments to theories unifying it with gravity. As we harness its principles, we may unlock interstellar travel, conscious AI, or even answers to the universe's origin. The quantum revolution is just beginning, reminding us that the universe is far stranger and more wonderful than we ever imagined.